So thanks a lot for this introduction. First of all, I would like to thank all my collaborators on this work, from the I2M lab in Bordeaux, of course, from the CEA and from the ESRF, and especially the PhD student Quentin, who worked on this topic during 3 years. So ceramides are well known to be very brittle and difficult to machine with a very low toughness, but it's finally quite attractive material for specific application, especially for defense in space, because under extreme loading and the dynamic regime, comparatively to other materials, it's quite interesting with very good properties, even if we have this kind of fragmentation mechanism. So the challenge for this material is still remaining to try to understand the strain rate sensitivity in relation with the microstructure to improve predictive capabilities with the different models. Because in the literature, this kind of diagram is well known, which concerns the evolution of the fracture stress or the limit strength as a function of the strain rate. This kind of evolution during a dynamic regime with a quite increase of the fracture properties is well known in the literature. And the explanation is possible due to micromechanical model by numerical prediction. So we explain this increase because of the link of heterogeneities, microstructure, therefore, and the dynamic effects of damage and dynamic loading. But finally, it's quite complicated, especially for brittle ceramides, to try to describe experimentally the evolution of the microstructure under dynamic regime. So that is probably a crazy challenge, but we work on that to try to describe the evolution of the microstructure at very small spatial and temporal scales during the dynamic loading, to try to explain and to corroborate the numerical model which has been proposed by COHEN in 2014, or more recently in the lab by Vincent Lochon. So the methodology is to try, first of all, to control the microstructure of porous alumina. We will talk about that just after with the manufacturing process in the material. We use a specific specimen geometry, which is a modified Brazilian test. I will talk about that later because we well known this kind of specimen geometry in the lab. This interesting thing is that this kind of geometry is well possible to apply dynamic loading with a split Hopkinson bar. And finally, we are lucky to try to have used ultra-fast X-ray radioscopy in the ESRF, and it was possible to follow the fragmentation with an information about the microstructure, even if it's only radioscopy in dynamic, because tomography is not possible with this kind of fracture time, but it was possible to have radioscopy. So about the microstructure and the manufacturing process, we use a gel casting process with the industrial collaborator. So it was possible to manufacture very complex geometries. First of all, we have a preparation with ceramic powder, of course, and polymers to have a specific microstructure. In our case, you would like to control the size of and the morphology of the microstructural defects. And in our case, it was porosity. So after molding and sintering, it was possible to have dense ceramides with a specific mechanical behavior. So the choices we made about the material, first of all, we are focused on dense alumina because it's a cheaper ceramides, and we have a lot of information in the literature for this kind of material. So we have a dense alumina with a very low porosity rate. We have other two alumina, porous alumina with a 20% porosity rate. The difference is the type of the pore and the geometry. We first of all have a microporous alumina, which is obtained by sintering the mixture. And the other possibility is to have a mesoporous alumina. This was very interesting because we have spherical pore, which is obtained by using polymer preforms and by sintering at the good temperature. And the last porous alumina we worked on is the 60% porous alumina, which is more like a foam behavior. Okay, so we have, of course, studied the microstructure in 3D with X-ray microtomography. We have a good evaluation of the microstructure with statistical evaluation. An example here for 20 meso and 60 meso, we have small pores which are very spherical geometry, and sometimes we have some interconnection due to the polymer preformed in the mixture. So that is why we have some large pores in the microstructure due to the interconnection. So what about now on the mechanical behavior in dynamics? So as I said before, we use a specific modified Brazilian test geometry with specific platons. Because it's well known for brittle materials that we can have a stress concentration just here during the mechanical loading. So by using this kind of flattens, it's well known that we can concentrate the maximum stress near the center of the specimen. But as we worked on porous alumina, by introducing a hole, a specific notch, a defect, an artificial defect, larger than the porous defect, it was possible to be sure to initiate the crack at the center of specimen. So finally, it is possible to estimate and calculate the tensile strength by considering a geometrical factor to consider the specific geometry of this Brazilian test. So as I said before, this kind of geometry is easy to apply to split Hopkinson bar in dynamic. So this is what we made. So it's very classical, and we use a specific Kolsky post-processing to estimate the forces and the stress applied to the sample. The particular thing we have made in this study is to do this experiment in the ID19 at the ESRF. So it was possible to follow the fragmentation of the specimen with a specific radioscopy. So we have the X-ray signal, and we use 2 high-speed cameras to follow the fragmentation of the cracks at approximately 4 million frames per second. So you have an example here with the 20 meso porous alumina. You can follow the porosity just over there. And what is interesting, I don't know if you follow that, but we have a main first crack just over there in dynamic regime, and after you have the global fragmentation of the specimen. So it was interesting to follow that and to be sure that we can initiate one main crack before the global fragmentation of the specimen. So of course it is possible to estimate the strength of applied just before failure, but we have to be sure that we have a quite equilibrium between the force in the different bars. So we just have checked that. And finally, we can evaluate first of all the fracture stress as a function of the porosity rate just over there, as it is expected. The bigger the porosity rate, the lower the tensile strength. As we can check just over there. And with this test, as we have isolate just a main crack in dynamic regime, it is possible by using dynamic fracture approach to estimate the dynamic fracture energy. So that we have done. So we isolate one crack, which was followed to estimate the crack path history. So the crack length as a function of time. During the propagation, we can observe that we have a quasi-constant crack velocity. That means that we have a stable dynamic propagation regime. And if we have that, it is possible to estimate rigorously the dynamic fracture energy. So about the crack velocity, it's very high. because we are working with ceramides. So we can see that we have an estimate of the crack velocity of about few kilometers per second. Of course, it depends of the density of the materials. So the lower the density, the lower the crack velocity. But when we estimate as a function of the Rayleigh wave speed of the material, we can observe that we have a maximum velocity for 3 materials, which is about 60% of the Rayleigh wave speed, which is known to be the maximum velocity before macro branching, as Elisabeth Joffé said in 1950. And for the more porous alumina, we have a lower velocity, but of course it is due to the microstructure of the material and the lower the higher porosity. So that's interesting because we have a test in mode 1 in the maximum velocity, so we can measure and estimate the fracture energy. So to do that, if I have more time to explain a little bit, we use a classical simulation with finite element method. This kind of methodology is well known. We use a generation phase simulation. So the input of the model is finally the crack path history, the crack velocity. And by doing that, it is possible to make a global energy balance to estimate the fracture energy and finally the energy consumed by the crack during the dynamic regime. The more important thing in dynamic regime is that you have dynamic effects due to the dynamic crack propagation. You have inertial effects and therefore kinetic energy created during the crack propagation. So you have to consider this part of kinetic energy, which is not equal to 0 at this kind of velocity. And by doing that, it is possible to estimate the fracture energy. So finally, we have the fracture energy by making global energy balance with the different energy parts. And we have to consider dynamic correction factor to estimate the fracture energy. So by doing that, it is possible to estimate the fracture energy as a function of the porosity rate. And we have some value obtained by numerical simulation, but by considering experimental data. So as you can observe, we have a decrease of the fracture energy as a function of the porosity rate. But of course, the value depends strongly how you estimate the fracture energy, how you consider the dynamic effects. So by our approach, we have the value just over there, and we found some very low fracture energy. Another last thing, maybe in this presentation, is about microstructure and fracture analysis, because post-mortem, is it possible to refine all pieces of the specimen? Because we have all in the small box during the propagation, and it is possible to reconstruct the specimen and to try to find the main crack and to follow the fracture mechanism locally. So we have made a different observation with electronic microscope. So just near the hole in the crack initiation, and we can observe some specific mechanism just over there with microcracks near the hole. And of course, classical transgranular and intergranular fracture. And we have observed the fracture surface just near the middle of the specimen, in the smooth part of the fracture surface in the dynamic regime, which is quasi-permanent. So in this quasi-permanent regime, we do not observe any microcracks in the volume and only smooth fracture surface with the same local mechanism at the grain scale with transgranular and intergranular mechanism. So to conclude on this presentation, so first of all, we have made some dynamic fracture tests using a very special instrument in the ESRF on the ID19 beamline. It was possible to study the influence of the porosity rate on the fracture properties. We were able to follow a dynamic propagation at few kilometers per second. So it's quite interesting by using this specific device and by considering the radioscopy. So it was possible to see if we have only one initiation of the crack or if we have a lot of crack propagation at different places in the specimen. So finally, we follow a stable dynamic propagation regime, and it was possible using a numerical simulation to estimate the fracture energy in a dynamic regime by taking into account inertia effects. So thanks a lot for your attention.